Right. Welcome to lecture today. I know there was a lot of excitement last night and this morning, and oof, a lot of uncertainty is still left with us. So we're going to focus on switching to a new topic and lecture today. We're going to be beginning a module on correlation and linear regression. Maybe I can get all of you in chat to leave off discussion of the election, just so we could focus on the class topics. All right, so here's the plan for what's coming up. I want to teach you about linear regression. We've been teaching you a bunch of topics. Linear regression is one of the really cool topics from this class that is super useful, used in all sorts of disciplines, and it's a way of making predictions about the world. Whenever we have an association that's a linear association, in other words, if you were to plot it, it'll kind of like a line. We can use linear regression to make predictions. So for instance, if you want to predict the amount of gas you're going to use on your next trip in terms of the number of miles you're going to drive on the highway, you would expect there's probably a linear relationship between those two. You could use linear regression if you had measured a bunch of past trips where you measured how long you traveled and how much gas you used to figure out what that linear relationship is, and then make a prediction for your next trip. If I'm going to travel 200 miles, how much gas do I think I'm going to use on that trip? So we're going to build up there slowly. And today we're going to talk about correlation, which is a way of quantitatively measuring the degree of association if there is a linear association. And then we'll work from there. We'll work with predictions. We'll look at fitting lines to a scatter plot, figuring out the best linear association that seems most consistent with the data, using that to make predictions. So that's kind of where we're heading. But we'll get there. We'll get there. Okay. So let's start by looking at one way you could make predictions given some historical data. Let's say we have some historical data about how things have turned out in the past, and we want to now make a prediction about how things are going to go in the future. Usually we have incomplete information, and we're making the best guess we can about how things are going to turn out. One way of making a prediction, let's say you're a doctor and there's a patient who comes in and they have some blood test results, and you're trying to predict what the diagnosis is, or what the risk is, or what the future will hold for that person. One way to make predictions is, if you want to make a prediction for some person, is to find others who are like that person, who are similar, and where you know how things turned out for them, maybe in your historical data set. And then what you do is use those outcomes as a basis of your prediction for this person. All right, so the idea is if people are similar, then they'll probably have similar outcomes. So if I can find similar people who have a known outcome, then that'll help me make a prediction for the outcome of the person we're looking at right now. Okay, so let's work through some examples. Let's do some demo and see how this works out. See how we could apply this. All right, so we're going to work with Galton's data set. Remember that one? This is that creepy guy who was all into like eugenics and, you know, crafting the future master race. I mean, really weird stuff. But one of the things that he was looking at, well, gee, could we raise taller kids? And he wanted to know what the association was between the height of the parents of a kid and the eventual height of that kid when they grow up to be an adult. So like, if I have a kid, you know, I'm kind of tall, but not super tall. How tall is my kid going to be? All right. And so Galton's idea was that he thought the heights of the parents would probably be useful for predicting the height of the kid. That makes a lot of sense. If you have like two really tall parents, then it makes sense to imagine, oh, it's maybe more likely that their kid will be really tall too. So he gathered a data set to try to measure whether that actually happens in real life. And he gathered data on a bunch of families where he measured the heights of the parents and also the eventual height of their kid when their kid grew up to adult age. And so the child column here is going to have the height of the kid. And as a reminder, this mid-parent height, what that refers to is we're taking the height of the father and the height of the mother, and we're averaging their two heights because we figure both their heights matter. All right. So he was imagining if the mid-parent height is higher, then the child's height is probably higher. So let's see if that seems to be the case. Anytime you got a data set, a good place to start is by doing some exploratory analysis. Just try to visualize what's happening here. So let's do a scatter plot. This is a scatter plot of on the x-axis the mid-parent height, the height of the parents, and the y-axis is the height of the child. All right. So looking at this scatter plot, maybe send me a message in chat. Do you think there is an association here? Yeah, looks like an association, maybe a weak association. I'm with you. Yep. It's not super strong. The points are kind of scattered around, but it kind of looks like it. When the parents are really tall, 74 inches, what is that? 6'2", I guess. Then it's kind of scattered around. There's a range of child heights, but this range looks a little bit higher than the range that we see when the parents are relatively short. So it kind of looks like the taller the parents are, the taller the kid is, but there's a lot of variation. There's a lot of randomness here. So now Galton wanted to make predictions for a new couple that are about to have a kid. He knows the height of the parents and he wants to make a prediction about how height their kid was. And he was doing this for these really weird reasons. He was like, wow, what if we can, pair people up to have taller kids or something like that. The measurements taken at a certain child age, they were taken when the child has grown up to their full height to adulthood. Yeah. Okay. So here's how we're going to do prediction. We're going to use this principle I just described. So if we have a couple and we want to predict how tall their kid's going to be when their kid grows up, we're going to look for other couples in this data set who are similar. And what would be a measure of similarity? Well, here the way what we're looking at that seems relevant about a couple is the mid-parent height, the average of the height of the father and the mother. So we're going to look for other couples who are similar in the sense they have a similar mid-parent height. And we're going to look at the height of their kids. And we're going to use the height of their kids to predict the height of the height of the kid of this new couple. And there might be multiple similar couples. So if so, what we'll do is we'll take all the similar couples. We'll look at all of their kids, the heights of all their kids, and we'll just take the average. All right, so let's code that up. Let's see. We've got a couple whose mid-parent height is H, and we're trying to make a prediction about the height of their kid. So I guess we're going to find other couples. Well, let's see if I can type in the right spot. We're going to find other couples whose heights is similar. So we want other couples whose mid-parent height is similar. And similar in this case, I'm going to say between half an inch shorter to half an inch taller. We will find all of those couples. We'll put that in a table called close points. We'll extract the height of their children, and we'll take the average of that. And that'll be our prediction for this new couple. So I put that in a function so I can call it many times. And then I'm going to work on my data set here by applying this to every couple in the data set. So this is a little weird, but we have historical data for all of these couples, and we're going to see what predictions we would have made if we hadn't known the height of their kid. Galton did collect the height of their kid after the fact, but let's figure out what prediction this approach would have made, if that couple, the height had not been known. And then we're going to visualize that. So let's visualize both in blue here. What we have is the observed height of the child, and in yellow is the prediction that this method would have made for that parent. So you can see here that this yellow, it's kind of like a straight line, more or less. It's a little crooked. And the taller the parents, the higher the prediction we make. The shorter the parents, the shorter the prediction. So this is kind of consistent with what we were imagining before, and it kind of makes intuitive sense that the taller the parents, the higher the prediction you'd make. So this is one way you could do prediction. Can I show you the code? Sure. Here's the code. The code finds for a given couple, we find other couples that are similar in terms of mid-parent height. We take the average height of their children. That's the prediction for this couple. So the yellow is the prediction. The yellow is the average of similar couples, of the heights of the kids of similar couples. So that's the prediction that we would make with this method. Okay, so this is one way to do prediction. This is not linear regression. This is sometimes called nearest neighbors prediction, and it's a perfectly reasonable way to do a prediction. Now, this method of prediction, you'll notice that the prediction is more or less, is kind of almost like a line. So you might be hypothesizing at this point, oh, actually, I bet that should be a straight line. This method of prediction is not taking into account that information that it sort of would make sense if this is a straight line. So when we build up to linear regression, we're going to find a way of making predictions that's going to ensure this is a straight line. And that will give us, if we don't have a lot of data, that'll often give us better predictions. So why ½ an inch? That was totally arbitrary. It was just an arbitrary notion of similarity. I could have chosen plus or minus 1 inch. It's just an arbitrary decision. There's really no justification I can give you for that. Okay. So that's a method you could use for prediction. I want to talk now a little bit about association. All right. So we've talked before about what it means to have an association between two variables. The way you can test visually whether there seems to be an association between two numerical variables is you can plot it on a scatter plot and look if there seems to be some kind of a trend. And basically, if the line seems to be going up as you increase as rightwards, then that's a positive association. And if the line seems to be going down as you right, that's a negative association. So an association is just a way of saying there's some kind of a pattern, there's some kind of a discernible shape in the scatter plot. It's not an amorphous set of points, but there seems to be some kind of a shape. So it could be a line, it could be this kind of like a bowl, it could be some kind of a curved thing that is a positive association but not a line. There's many kinds of association. And we're going to focus for this module on linear associations. One kind of association that's very common is a linear association. That's where it looks like there's kind of a straight line happening there. So for instance, the association between mid-parent height and child height that we're looking at would be a linear association. It looked like there was a kind of a line there. The points were kind of scattered around, but they were kind of scattered around this line. So that's a linear association. You can also have nonlinear associations. That'd be any association that's not a line. Like if the points look like they were scattered around some kind of a bowl shape, that would be an example of a nonlinear association. So what we're going to do, the approach we're going to take is we're going to first visualize the data to try to get a sense of what's going on. That's kind of a coarse way of understanding, getting some intuition for what's going on. Of course, visualization is unreliable. It's subjective. Sometimes we can see patterns that aren't there. It's hard to pin that down. So then we're going to look at how to quantify the association. Okay. And the way we're going to quantify an association is using something called the correlation. So let me show you some examples. And this time I'm going to work with another data set. Let me introduce a different data set. This time we're going to look at a data set of different models of cars that have been on the market over a period of time. Okay, so here's the data set. You can see in this data set we have different models of cars and the year they were released, and MSRP, that's the manufacturer's suggested retail price. That's basically the price of the car if you buy it new. There's acceleration, miles per gallon, what kind of car it is. And yeah, you can see that there's some, very expensive cars in there, up to over $100,000. I would never pay that much for a car. This is not adjusted for inflation. This is an old data set from more than 5 years ago. This is just some example data set. Don't take it too seriously. All right. So let's look to see whether there's an association between the miles per gallon that these cars get and the price of the car. So on the x-axis is miles per gallon, and on the y-axis is MSRP. And here I've made a scatter plot. So why don't you leave me a private message in chat? Do you think there's an association? And if so, what kind of association? Is it linear association or nonlinear association? Okay, good. Good. So yeah, I'm with you. Association, I agree. There's an association here. It looks like there's an association here where cars that get a higher miles per gallon have a lower cost. Is it linear or nonlinear? I don't know. You could be thinking it's kind of looking like this. Is this right, or am I flipped? I don't know if my video is flipped or not, but it's kind of the shape. I think I would, when I look at it, it looks a little curved to me. So to me, I would be thinking nonlinear. I mean, no guarantee, but it kind of looks like it's going a curve shape. So I would say nonlinear here. I'm flipped. Okay, so it should be like this. All right. So there's an association here. Does that make sense? My first thought was I would have guessed that like getting better miles per gallon requires better technology engine, and you have to have the more modern stuff, and it'd be more expensive. But that's not what we're seeing here. Actually, the better mileage are getting lower price. So why is this? Anyone want to take a guess on why that might be? The Prius is way out there on the right, and it's also relatively cheap. People like fast cars, zoom fast. Totally. Yeah. So what's happening over here on the left side? You're getting cars like sports cars, pickup trucks, SUVs. Those are more expensive. They're bigger cars, and they also guzzle gas. Totally. Smaller cars have smaller engines, get better mile per gallon, and cost less. And the bigger cars eat more gallons of gas and cost more. Okay. So makes sense in retrospect. All right, let's do another one of these. Let's look at acceleration versus price. Let's see if there seems to be an association. So what do you think? Why don't you tell me now whether you think there's an association or not, and linear or nonlinear? Yeah, linear association. To me, this looks like it's kind of a straight line here, and the points are scattered around that. They're not exactly on the line, but it does look like there's a positive linear association. Good. And that kind of makes sense that these higher acceleration vehicles, maybe they're bigger engines, bigger cars, bigger trucks, or maybe they're sports cars, and you would kind of expect those. Okay, it makes sense that those cost more. All right, and maybe part of what's going on here is SUVs, right? SUVs are particularly expensive. So let's focus in on SUVs, and there's 39 SUVs in here, and we could look just for the subset of SUVs at the relationship between acceleration and price. Now, if I look at that, it's a little less clear. I'm thinking maybe there's still some kind of a linear association here, but I'm not entirely sure. It's a little hard to tell visually looking at it. So sometimes it can be a little hard to tell just by visualizing. We could look at the price in the miles per gallon for SUVs, and that looks clearer. That looks like there's some kind of a negative association there. All right, so we're going to talk about how to measure this, how to quantify how strong an association is. If it's a linear association, if we suspect a linear association, I'm going to show you the notion of correlation, and we're going to introduce a correlation coefficient. And a correlation coefficient is a way of measuring how strong a linear association is. And this gives you a way to quantify so you don't have to be so reliant on subjective stuff. So to set things up for that, what I'm going to do is I'm going to first show you what happens if we convert all of these numbers to standard units. So we talked about before, some cases using standard units can be helpful because it helps us show the variability. People were asking here what the units are. And in some sense, for correlation, I don't really care what the units are. I don't care whether those are thousands or tens or millions or dollars or pounds or euros. It doesn't matter. The shape of the graph is the same either way, and it's the shape that determines how much of an association there is. So let's look at how to convert these to standard units. As a reminder, how the way you convert something to standard units is you find the mean and you find the standard deviation, subtract off the mean. So you've moved the mean to 0, and then you divide by the standard deviation. Okay. So if we have an array of values, we're going to find the average, the mean of all the values in that array, and subtract that off. So they're now centered around 0. And then I divide by the standard deviation of those values. And that kind of squishes them together so that values that are 1 standard deviation above the mean become +1. Values that are 1 standard deviation below the mean become -1. Values that are exactly at the mean become 0, and so on. And that will convert an array of numbers into standard units. Okay, and now I'm going to redo these same plots, but this time with using standard units instead of the units in the table. Okay, so let's see, what was the name of my table? SUV. Price. Okay, so I've created a new table where I converted everything to standard units, and then now I plot the scatter plot between miles per gallon and price. And I want to try to help make it easier to see what's going on here. So let's see if I can make things a little smaller so you can see. I just want you to look at the shape of the plots. So don't try to read the text. I know the text is really small. So at the top, we have the scatter plot of miles per gallon versus price for SUVs in normal units. And in the bottom, we have that plot after I've converted everything to standard units. So what do you notice about these two plots? Squished, squished. Shape is the same. It's exactly the same shape. It's exactly the same shape. And why is that? That makes sense. That kind of makes sense when you think about what standardization does. In standardization, I subtract off the mean. I subtract off something from every point. If I subtract something off from every point, that's like moving it left or right, or moving everything up or down. All the points move left or right or up or down the same amount. So it keeps the same shape. It just kind of like moves around where it is on the graph. And then if I divide by something, dividing all the values on the x-axis by something kind of squishes them together or stretches them out, but it's still the same shape. It's like zooming in or zooming out. And the same for the y-axis. I've stretched them out. So basically what I did is I took these values on this plot and I kind of shifted them over to 0 and I squished them together so they're around plus or minus 1. So it kind of moved them. And then this new plot down here is plotting a different region. It's plotting the area around 0. And so you get the same shape. All right, so same shape, standard units, doesn't change the shape at all. So it shouldn't change the association at all, but it's useful for us. It's going to be useful for us in a moment for measuring the extent of the association. And you can see this is a negative association because smaller values of miles per gallon correspond to higher values of price. Okay. We could do that again with now looking at the association between acceleration and price. And here again, there's these same two plots. At the top is normal units, and at the bottom is standard units. You can see it's exactly the same shape. We've just scaled things and moved things around, and you squished them or expanded them all by the same amount. Hope that makes sense. Okay. Let's zoom back in, see how we're doing. All right, so now I'm going to introduce the correlation coefficient, which is a measure of the amount of association if you have a linear association. So this is only applicable if you have a linear association. If you have a nonlinear association, you got to ignore everything I'm going to say for the next few lectures. Fortunately, linear associations are really common. All right, so the correlation coefficient is this standard quantity. It's standard in statistics, and I want to teach you how to calculate it and how to interpret it. And it's typically called R. gas, just the standard letter that represents the correlation coefficient. It's a measure of linear association. How much linear association is it? Is it a weak linear association or a strong linear association? So intuitively, the relationship between the mid-parent height and the child height was a pretty weak one because we had this prediction line. I guess it was like this, but points were scattered all over the place. They were not tightly clustered around the line. So that was a weak association. So that would have a very small value of R. If there's a very strong association, points are clustered very near the prediction line, then that would have a large value of R, meaning there is a high correlation. So correlation is a measure of linear association. And the way we compute it is we compute it by first converting everything to standard units, and then we do this mysterious formula. So you just got to memorize this procedure, this formula. And then I'm going to give you some intuition for why it might be a sensible thing to do, but it's just a standard thing to do that you just got to accept and take on faith. And this formula is going to give me a number. We call it R, the correlation coefficient. It's between -1 and 1. Okay, so +1 means a really strong association, and it's a positive association. -1 means a really strong linear association, and it's a negative association. And 0 means no association at all. Okay. All right. So let's look at how this works. Let's do demo. So I wrote some code here that will generate a scatter plot of points that have a particular value for R, a particular value for correlation coefficient. So here would be an example of some points that have a correlation coefficient of -1. You can see that's a linear association. It fits to a line that has a downward slope, and the points are essentially all on that line. So it's a very, very strong association, very strong correlation. All right, so R is -1. I'll show you +1. There's +1. Now we've got another very, very strong association. This time it's a positive association. And the points are essentially all on the line. They're very tightly clustered near the line. So that's a very strong association. Let me show you uncorrelated, no association. There are a bunch of points that are uncorrelated. There's no association here at all. Larger values of the x-axis don't tend to lead to larger values on the y-axis. So we call that uncorrelated, or correlation coefficient is 0. I defined the R scatter function at the very top of this notebook. You don't need to know what it's doing. All that you need to know is this is some magic code we wrote to give you examples of data that would have a particular, constructed to have a particular correlation coefficient. So yes, you're absolutely right. You decide whether or not this is a strong or a weak correlation by computing the correlation coefficient R. You look at the absolute value, and if that's close to 1, then it's very strong. And if it's close to 0, then it's very weak. All right, so let's do another example. Let's do, instead of 1, we're going to do correlation coefficient of 0.9. So that's still quite a strong association. There's a clear line here, and the points are pretty close to that line. It's not quite as strong as R equals 1, but it's still quite strong. The points are quite close to the line. So that would be a pretty strong correlation coefficient. Here would be a correlation that is less strong, R 0.5. You can see that there is still an apparent trend here, but the points are now more far apart, more scattered apart. So that is a weaker association. And I'll show you a really weak association, R equals 0.1. And visually, to me, that looks uncorrelated. I can't discern any trend or pattern here, but there is a very slight positive association here. It's very weak. There's a lot of noise. The points are not scattered close to that line at all. You would not be able to tell this visually, probably. You would have to use these quantitative methods to identify the correlation. And these kinds of correlations, even though they may be hard to spot visually, can still be quite important. They can be quite important for prediction. They can identify some patterns. For instance, maybe you have a bias here. If there's a correlation here between outcomes and income of the person, then that may indicate there's some kind of a systematic societal bias in your system. All right. So close to 0 is a weak correlation. 0 is totally uncorrelated. Close to +1 or -1 is a strong association. Someone asked about the slope. The slope of the line is not what's important here. What's important here in terms of how strong or weak a correlation it is how close the points are to the line. So that's what we're trying to measure. We're trying to measure like how well do the points fit that line or cluster around the line. So 0.1 is a positive association. It's correlated. It's just very weak. It's very, very weak. Okay, so this is a correlation coefficient. Are correlation and association synonymous? Basically, yes, except that when I hear the word correlation, I think of a linear association, whereas an association might be linear or nonlinear association. If you look at the notebook, R scatter was defined at the top of the notebook. It's just some code we wrote. Don't worry about it. This is just to give you visualizations. It's not, you don't need to know what that code is. Okay, so let me tell you how you compute the correlation coefficient. That's some intuition of what it's measuring. Let me show you how you compute it for a data set. If we didn't construct it, the data set especially, but we have a data set, here's how you compute the correlation coefficient. You convert, you have these X and these Y values that we have on the scatter plot. You convert the Y values to standard units. You convert the X values to standard units. So you put everything in standard units and you do a scatter plot in standard units. That'll still have the same shape. Now we're going to compute the correlation coefficient on that plot. And what we're going to do is we're going to take, for each point, we're going to multiply their X value and their Y value, but the standard unit version of those. We're going to multiply those for each point. That gives me a number for each point. And then I'm going to take the average of all of those. Now, this might sound a little weird, but this is the formula. So, and when you do that, that gives you the correlation coefficient. This is going to measure how closely clustered the points are to the prediction line. All right, so let me show you an example of how we would compute this. Actually, I want to give you an idea of why this is maybe a reasonable thing to do. Let's say we have a positive association like this. So there's a positive association. You can notice in standard units, 0, 0 is at the center. Now, when the X value is large, when we're on the right side of this picture, in this case, the Y value is also large. Well, positive in any case. So positive X values tend to go with positive Y values. And negative X values, the left side, tend to go with negative Y values, the bottom side. So when you multiply the points on the right-hand side, there in the upper right, you're multiplying something positive times something positive, and you'll get a positive number for these points in the upper right. And the points in the lower left, you're going to get negative times negative, you're going to get another positive number. So most of the numbers that you get for these points are going to be all positive, and you take the average of them, and you average of a bunch of positive things will be mostly positive. There aren't many numbers you get this way that are negative because there's not many points that are in the lower right. Lower right would be positive times negative, or upper left would be negative times positive. That would be ways you could get negative numbers, but there aren't many points that are in the upper left or the lower right. So there aren't many points that'll have a negative number associated with them. So when you take the mean, most of the points will be positive and a few will be negative, and the mean will be mostly positive. And so that's makes sense that for this shape, the correlation coefficient you got by this formula would be a positive number. Okay, so let's see how you calculate this by doing an example. So here's a very simple data set. I just have a small data set that has a shape that looks like this. So that's 1, 2, 3, 4, 5, 6 points. They just artificially made them up, and we're going to compute the correlation coefficient for this. Now, is there a linear association here? I don't know. Hard to say, not an obvious one, but let's measure the correlation coefficient. So the first step in measuring the correlation coefficient is we convert to standard units. And I'm going to show you a scatter plot of that. Same shape as we had before, but now in standard units. So at the center of this graph is at 0, 0, and we're going from well, everything's in standard units here. And then what we do is for each point, we take the product of its x value and its y value now that they're in standard units. So like this point up here is about x value of a little less than 1.5 and a y value of maybe 1.7. And so the product of those is going to be 1.5 times 1.7, something positive. So let's do that for all the points. We're going to compute the product for each point. It's the product of the x and the y in standard units. And you can see there's some of these points, have positive values and one has a negative value. And now we take the average of those products. And here the average is 0.6. And so that is R. That is the correlation coefficient. So for this data set, the correlation coefficient is 0.6. Okay. So if I put this into a function, here's what the function looks like. The procedure is convert the data, both attributes, into standard units. For each point, multiply the x value and the y value. Multiply the two attributes. We're looking at the product, and then take the average of those products. And it just so happens that that's always going to give you a number that's between -1 and 1 and measures how much linear association there is. Okay. So for this simple data set, the correlation coefficient for x and y was 0.617, saying that there is some kind of linear association there. So now we can go back to our data set of SUVs and look at the correlation coefficient between miles per gallon and MSRP, and that's negative. That's saying that there is a linear association here. It's a negative association, which means that increasing miles per gallon is associated with lower price, which we discussed before. And we can look at the correlation coefficient between acceleration and price, and we see that's a positive association, that cars with higher acceleration also tend to be more expensive. And this is a quantitative measure of how strong the association is. So this is very widely reported in, for instance, social science literature will report the value of R, and that will help you interpret how strong an association is in numerical terms. Or they may tell you the value of R squared. That's just the square of this. So instead of 0.486, they might tell you the square of 0.486. Okay. So is there a function that does this automatically? No, but we just wrote one. So we just wrote code to do it. It's not that hard to do. It was a couple of lines of code. So if you need it, you can copy paste this code, and then it'll compute the correlation coefficient. All right, that's the definition of the correlation coefficient. Let me give you some thoughts about how to interpret it. Generally, use the correlation coefficient to determine how strong or weak an association there is, and if there is a linear association. But just some things to be aware of. When you have a data set, you suspect there might be a linear association. You can use the correlation coefficient to try to get a sense of whether there is one, but be careful. Just because there's an association doesn't necessarily mean that there's causation happening. Remember, you can have an association without there being any causation, for instance, because of confounders. Beware of nonlinear associations. If you have a nonlinear association, the correlation coefficient is misleading or not useful. It doesn't measure how strong the association is. It's only useful for linear associations. Beware of outliers. If you have outliers in your data, just a handful of points in the data set that have values that are wildly different from everything else, those can really skew the value of the correlation coefficient and mess things up. And finally, ecological correlations. And I'll tell you what each one of those are. So I want to give you some examples of each one of these pitfalls. The general point, though, is correlation coefficient is a way of detecting linear association and measuring how strong it is. All right, so let's look at these pitfalls. Oh, yeah, I wanted to show you what happens. I'll tell you what each one of these are. I wanted to show you what happens if you switch the axes. The correlation, we had the correlation between x and y. What about the correlation between y and x? So I've got this plot, but I can reverse the role of x and y, and it's a different shape. But the correlation coefficient is the same. Okay, so the correlation coefficient is symmetrical. For instance, if I have the correlation between acceleration and price, I could also compute the correlation between price and acceleration. And that's exactly the same value. And it kind of makes sense. If larger values of acceleration are associated with larger values of price, then larger values of price are associated with larger values of acceleration. So it's just kind of testing that this has a property you might expect. All right, so let's look at nonlinearity. Here's an example data set that has an association, but it's a nonlinear association. You see that kind of a bowl shape? That's definitely not a straight line. That's curved. But there is a very strong association there. It's just not a linear association. Now, if we compute the correlation coefficient for this data set, the correlation coefficient is 0. So you might say, oh, no association, but you'd be wrong. Be careful. This means there's no linear association, but there could still be a nonlinear association. In this case, there is a nonlinear association. Okay, so that's one thing that can go wrong with using the correlation coefficient. Make sure you visualize the data first to check to see if it looks like there's some kind of a linear pattern before using the correlation coefficient. Otherwise, it may be misleading. Another pitfall is outliers. So here's a data set where the data is kind of all on a line, and the correlation coefficient, therefore, is 1, saying there's a perfect linear association. But now, let me add one more data point that's kind of a wildly different value. Here, the y value is wildly different. And look at the correlation coefficient. And now the correlation coefficient is 0, claiming that there's no linear association, when actually 4 of the 5 points do fit a linear association. And you can have more extreme versions of this where you have 999 of your 1,000 points fall perfectly on a line, and 1 point, one outlier, that is just way far away. It's like down below, beneath my feet, beneath the ground, way far away. And that 1 point has an enormous influence on the correlation coefficient. The correlation coefficient says 0 or says -1 or says +1. So one outlier can have just an inordinate effect on the correlation coefficient. So when you visualize your data, check if there appear to be outliers. This would be an outlier. And if you see an outlier, you might either need to interpret the correlation coefficient with care, or maybe remove the outlier from the data set before you compute the correlation coefficient. I see some questions. Does strong mean the pattern is strong and the association is strong? Yeah, kind of both, right? Like it means that there's a linear trend, and that the points are very, very well fit by that linear trend. The points are clustered around that linear trend, that there's not a lot of noise in it, that mostly you can explain what's happening in the scatter plot by saying the points are near this line with a little bit of noise, but not too much. Okay, so a strong association is one that like there's a really strong pattern. And a weak association is a very noisy pattern. There's a lot of noise in it. You know, there's a little bit of a trend, but there's also something else that's having a large effect. It's not just this association. So yeah, sometimes people recommend that if you're doing linear regression, looking for linear associations, if you want to find any kind of a linear association, if you have a few outliers, you might remove them. It's a little dangerous because maybe that's really important data, but sometimes outliers can happen. For instance, if someone jots down a number wrong, they're recording the data, and the number should have been 103.2 inches, but they inadvertently skip a digit, and so they write down 13.2 inches, and now they've got a number that's wildly different. So sometimes outliers can represent measurement error, or just a weird case that's not really what I want to model. You know, Michael Jordan or something like that, his salary is an outlier. So sometimes it makes sense to remove the data. Sometimes it's a little dubious to do so. So you're going to have to use your judgment. I can't give you a hard and fast rule. You got to look at the data, understand what's going on with that data point, figure out what makes sense for your particular application. All right, ecological correlations. I mentioned this and someone asked, what is it? And I want to give you an example. So we're going to look at SAT scores. And I think this is very relevant actually today. I don't know if you know, but in this past year, the UC Regents voted to eliminate use of the SAT score, phase out use of the SAT score in freshman admissions to UC schools, and look at replacements. And so let's look at SAT scores. And here's a data set. It's a little old, from 2014, that has broken down by state. For each state, there's some information, and the part that we're going to be looking at here is the average math score for all the students in that state. So for instance, the average SAT math score for all the students who took the SAT in Alabama was 538. And got that for critical reading and math and writing. So let's visualize this data set to understand what's going on. And here's a scatter plot that looks at the relationship between the math score and the critical reading score. And when you look at that scatter plot, holy cow, look at that. All right, strong association or weak association? Super, super strong. I mean, there's a line, looks like it goes through it, and those points are really close to the line. So this is a strong linear association, a very, very strong linear association. In fact, when I look at this, I think, why do we even need to give you both the math SAT and the critical reading SAT? Why don't we just give you one of those? And either one, the two scores are so super closely connected that why measure both? What extra information is that giving us? But there's something wrong with that reasoning, right? Something's fishy here. I don't know about what your SAT scores were like. Did you end up with an SAT score that had the math and the critical reading almost exactly identical? I don't know about you, I didn't. I mean, I did pretty well, but my reading was not good. So some of us, they might be exactly identical, but if we go ask a few friends, I bet we might find that for a lot of people, our scores might be quite different. So something's weird. Something is weird here. In fact, your math score is not a really good predictor of your critical reading score. It's not a super strong association between your math score and your critical reading score. Even though in the scatter plot, there's what appears to be a very strong association, correlation coefficient of 0.98. It's like ridiculously strong. So what is going on? How does this, I mean, it doesn't make sense, right? It doesn't we do some sanity check on a few people we know and no, this does not match what we see in real life. So is my data set wrong? It's because they're averages. Yeah, see what each data point represents here. Each data point represents not an individual, but a state. It's the average of all the students in that state. So what this is saying is not that your math score and your critical reading score is almost exactly identical. It's saying that the average math score in a state is almost exactly identical to the average critical reading score in a state. Now tell me why there might be a really strong association between these averages at a state level, even though there's not much of an association at the individual level for individuals. This is tricky. This is now where you get to think about your domain knowledge about SATs. Better education in some states than others. Yep, that's a really natural hypothesis, is that some states, their education system is just much better than others. Like maybe whoever this point is on the upper right, boy, that is the state to move to because they've got a great school system. But it's actually does not appear to be what's the case. It turns out what's going on is something a little different. It's those of you who said confounding factors, man, you are spot on. Wealth, yes. Does anyone heard of socioeconomic status? It turns out that when you measure almost anything in society, there's a strong correlation here to people's wealth, to their social status, like whether they're minority or not. People in wealthier districts have schools that are better, and people in poorer districts have schools that are worse. And people in white districts tend to have better schools, and minorities tend to live in areas with worse schools. And so what explains most of this pattern here is that wealth is not evenly distributed across the US. Socioeconomic status is not evenly distributed. So these states on the upper right are states that have a high socioeconomic status. They're really wealthy. And the states in the lower left are the ones that are really poor, have a lot of minority students. And so most of this variance at the state level is actually, it's explained by socioeconomic status. So even though at the individual level, there's no association, at the state level, there appears to be one. And this can be really crucial. For instance, I read a study once that claimed that um, charter schools were great because you looked at the state level, you looked at the states that had the most charter schools also had the highest SAT scores, which looked like really strong argument for charter schools, except that when you looked into it, you discovered that what was happening was this ecological fallacy, that the states that had more charter schools also tended to be the states that are richer. Richer states are more likely to have a charter school, and therefore also had higher SAT scores because the SAT is biased. It's biased by a socioeconomic status. And that was exactly one of the points that was at issue in this decision of the UC Regents. Okay, so I think we'll stop here. Those are some caveats to be aware of when you look at the correlation coefficient. We'll see you in lecture on Friday.